Hello everyone, my name is Hyunung Jang and I'm a PhD student in Texas A&M. This is joint work with my advisor, Dr. Kwon Jo. A directed acyclic graph can be used to visualize the data generating scheme among a set of variables. DAG model G can be expressed by a node set V and the edge set E without a cycle. DAG encoded a set of conditional independence relations among nodes that we can read off by the separation rule. There exist more than two DAGs that encode the same CI relations. We say that these DAGs are in the same Markov equivalent class. There is an exact graph instant called completed partially DAG, CP-DAG in short, that has one-to-one relation with a Markov equivalent class. First, from now on, we use two terms CP-DAG and Markov equivalent class interchangeably. Another characteristic of DAG is that there exists at least one topological ordering, meaning that if I is smaller than j, then the direction can be from sigma I to sigma j, not the other way around. The structural learning problem of DAG model start with a question. Can we recover the underlying DAG G star from which observational data X would have been generated? The score-based structural learning methods attempt to find a graph that maximizes the score or likelihood. There are a few challenges on the score-based structural learning. One is its enormous size of the space. A DAG space increases super exponentially with the number of nodes P. With 14 nodes, there are already more than 10 to the 36 labeled DAGs. Another challenge is irregular search space due to acyclicity. The other is the existence of Markov equivalent class. We cannot, this can cause non-identifiability, so it may affect the efficiency of the algorithm. Many algorithms choose CP-DAG space as their search space. However, the size of CP-DAG space is also conjectured to grow super exponential in P. Here is another building block of our work, mixing time. Mixing time of Markov chain is defined as minimum transition step that the distribution of chain is close to its stationary in total variation distance with an arbitrary initial state. If the mixing time grows at most polynomially in N and P, we say that the chain is rapidly mixing. If it can grow exponentially, we say the chain is slowly mixing. Complexity analysis of Bayesian method is important, but there is limited literature. Our main contribution is that we come up with a new metropolis Helsinki algorithm on a restricted space of Markov equivalent class and study its time complexity. We prove rapid mixing of algorithm under some high dimensional assumptions. To the best of knowledge, there is no literature that deals with mixing time analysis for structural learning MCMC algorithm before our work. Another contribution of our work is that we devised general path method, which can be generally applied to other high-dimensional model selection problems. The main intuition about the canonical path method is similar to that of deterministic local search. Now we introduce the intuition about making deterministic local search find the localmost G star in polynomial time. First of all, we need to specify the neighborhood relation with proper size. First of all, a local search neighborhood of G should be large enough so that we can have at least one element, G prime, that has higher score than the current state. Also, the local search neighborhood of G should not be larger as exponential because it may cause local trapping on G exponential time. Lastly, exponential length of the path G to G star would hinder the algorithm from having the polynomial complexity. In short, the how to choose neighborhood relation is critical. Specifying such local transition as this picture that generates a path from G to G star is a key step of the canonical path method. We can see the challenge on the constructing canonical path on CP-DAG space if we compare it with the canonical path of variable selection method. Yang et al. Suggested that add, delete, swap local move and prove the rapid mixing of MCMC. Finding the local transition of a state is straightforward in the variable selection problem. If an important variable is not included, adding the variable increases posterior score. If all of the important neighborhood variables and some of unimportant variables are included, deleting one unimportant variable increases posterior score due to the model size penalization. In our problem, finding a local transition rule is not as simple as the model selection case due to the complex nature of CP-DAG space. For given the topological ordering, estimating the DAG with the best score can be from a series of variable selection for each node from its ancestors in the ordering. However, out degree constraint of our model space can make it not as trivial as a series of variable selection problem. Also, we should be careful about a cyclic constraint because we consider the local move between the DAGs with different ordering. To introduce our main result, we define some basic notations and notation for the true generating model. You may stop here for a minute to understand them. Now we propose our algorithm called random walk greedy equivalent search to sample from posterior distribution on equivalent class space. To explain our algorithm, we need to specify two components of the algorithm, a model space and a neighborhood relation. If we define a sparse DAG space as a collection of DAG with a maximum in degree and out degree is bounded by the parameter d in and d out, our model space, namely a sparse equivalent class, can be defined as the collection of all equivalent classes that contains at least one member in the sparse DAG space. Next, we'll define ADS neighborhood relation in the sparse equivalent space. First, we consider add, delete, swap neighborhood relation in the DAG space where a DAG with a edge addition, deletion, and swap from G belongs. The ADS neighborhood relation in CP-DAG space is the collection of CP-DAG which has at least one DAG that belongs to one of the neighborhood relations, add, delete, or swap. Note that without swap operation, RWGS can stop at the boundary case where the maximum degree of the graph is equal to D in or D out. Here is one concrete example of neighboring element. Note that the size of neighborhood is not trivial and it is time consuming. However, in practice, it is not necessary. To state our main result, we list up the set of assumptions. Assumption A is restricted eigenvalue condition, and assumption B to E specify the condition of prior parameters and degree constraint parameters. Lastly, strong beta mean condition guarantees the lower bound of the signal size for all permutation. Now we state the main theorem. We have polynomial bound for the mixing time of the RWGS algorithm with the order of right-hand side of the inequality. Thank you for listening, and our work can be found in arXiv.